Hi, everyone. Welcome to the Hudi Community Sync for October 25th. Today, we'll be going over the Hudi community stats and updates. After, we'll do a deep dive on the record level index. If you have questions after the community sync, feel free to ask them on the Hudi community Slack channel. So let's jump into the community stats. For the past month, from September to October, we've had over 65 PRs. We also had a major release, which is 0.14.0, which brought about the record level index, primary key auto generation, and querying incremental updates by using select star with Spark SQL. You can read more about the release on the release notes on hudi.apache.org under downloads. In terms of growth, we have over 3,600 users on Slack, over 4,600 GitHub stars, and we had about 36 contributors who contributed to the GitHub repo. We're working really hard on a 1.x beta release for November, so stay tuned on Hudi's socials or Hudi community Slacks for updates. We also have a new RFC, RFC 73, to support atomic operations across multiple tables. You can read more about the RFC in the description down below. We're definitely growing. If you haven't already, give us a follow on LinkedIn and Twitter. Please also start us on GitHub if you love and use Hudi. You can scan the QR code or visit hudi.apache.org to join the Hudi community Slack. And without further ado, let's talk about how the record level index works in Hudi. To recap, Apache Hudi is more than just a table format. It serves as a comprehensive platform designed for data ingestion and processing. It's equipped with a range of features and services aimed at maximizing the efficiencies of both writing and reading data. At the foundational level of the platform, we have the data lake storage. This is where all the data resides in various prevalent data formats like Parquet and Avro. These formats have been designed for efficiency and scalability, ensuring that your data is stored in a way that's both space efficient and also easy to access. Upon the base, Hudi provides a transactional database layer, which is the layer that you see above the open file data formats. This layer is where Hudi's true power shines as it offers multiple services, including table services, indexes, concurrency control mechanisms, amongst many others. But these services collectively offer significant enhancements to data and table management. Table services facilitate the handling of data at scale, indexes speed up retrieval of operations, and concurrency controls ensures consistency of data across multiple operations. But after data has been successfully ingested and effectively managed through the previous layer, which is the transactional database layer, Hudi offers the ability to connect this processed data with popular computation engines. So for example, one of the ways you can connect Hudi is with Trino or Presto to query the data and use that data to power your downstream applications or analytics. Today, we're actually going to be diving into the indexing table service in Hudi, which is part of the transactional database layer. And we're actually going to double click into specifically the record level index. So let's talk about indexing real quick before we double click into the record level index. Indexing is widely employed in database systems such as RDBMS and data warehouses to locate information quickly. I think a lot of us are aware of this. And this is similar to how an index page at the end of the book helps you locate information quickly. But in data systems, such indexes are used to reduce I/O costs and commonly used to improve query performance or write performance and so on. Hudi also uses indexes to locate records efficiently and do fast upserts. As you can see in the diagram, without an index to apply updates and deletes, each data file has to be merged against all the updates and deletes for that table. However, with index, Hudi merges each file with updates and deletes only for that file, and this significantly reduces the I/O for merging data. Hudi already supports different indexes for different use cases, and there are two popular use cases shown here. The first one is updating the dimension table for the user input. Usually these generate a lot of random updates spreading across most files in the table. Simple index is the best for such use cases. It simply reads the key and location from the table and then finds the location. And the second use case, the input events are mostly ordered by the timestamp. Most events fall into the last few hours and only a small portion of files are updated in the whole table. In such case, Bloom index is the best because it uses the Bloom filter co-located with the data files to prune files instead of reading all the keys. This significantly reduces the I/O if only a small portion of files need to be updated. For large-scale datasets ranging from tens of terabytes to petabytes, simpler Bloom index may still not be performant enough. And this is where HBase index comes in. Here, it's used to send key lookups to an external HBase table storing the key to location mapping. So the key lookup is blazingly fast. So as you can see, there are a couple of challenges for large data sets using existing files. The simple Bloom index needs to read either the keys or Bloom filters from all files. They have to read some data or metadata per file. This can be really expensive for large data sets, particularly on cloud storage, because cloud storage enforces rate limiting on I/O, which means that you can only send a certain amount of RPC calls to cloud storage to read data. So this can create bottlenecks to the index. And the HBase index, although it's very performant for like large data sets, a separate HBase cluster is actually needed to be maintained. And HBase is operationally difficult to maintain and scale for throughput. So that requires dedicated resources and expertise that you may or may not have, or your team may or may not have. Now the question comes in, can we design a new index to address both of these challenges? So the record level index comes to the rescue here to kind of address the challenges that we just mentioned. By design, the record level index stores the key to location mapping like HBase index directly to the table level metadata. To realize that, there are new partitions called record index that's created to internally to store the mapping and the index metadata in a few file groups instead of co-locating with other data files. So this drastically like cuts the cost of the file I/O. To make the storage footprint low, we designed an inefficient key to location entry. So a combination of random UID key and date string partition only takes about 50 to 55 bytes. And the record level index directly leverages the metadata table for fast index lookups and updates. So the metadata table is an internal MOR table which provides uniformly fast updates for different index metadata. And you can check out more about the metadata table with Prashant's LinkedIn live session that will also be linked down below in the description. So the H-file format of the metadata table unlocks fast point lookups. So now let's take a look at how the record level index metadata is organized on storage and how read and write works. The record level index is stored in a record index partition in the metadata table with multiple file groups, just like a normal Hudi table. And each file group contains multiple file slices, and the latest file slice reflects the latest snapshot. And if you're not familiar with Hudi's table format, that will also be linked down below in the description for more detail around that. Okay. So given that the metadata table uses the H file as the base file format, the H file contains the key to value pairs of the record key to location mapping. And so let's say, now we have a set of record keys to look up. The corresponding file groups are identified by the hash function. Then these keys are looked up in the H file through point lookups without having to scan the whole file, which is efficient. And when there are updates to the record level index, the metadata table internally writes new log files with the updates. And the log file uses the same log format with each data block using H file format. And during the lookups, both base and log files are scanned in a point lookup way. And the metadata table periodically compacts the file groups to make sure the performance of reading the record level index is good. We have done a few performances on the benchmarks on both write and read to demonstrate the performance benefits from the record level index. In the first case, we have 1 terabyte data set, and each write batch has 200 megabytes of random updates across the table. We compare the performance of the record level index, the global simple index, which is the best for random updates. We can see that the index lookup latency is reduced from around 20 minutes to 1 minute after using the record level index. This is because the record level index only has to read the metadata from a few file groups in the metadata table, while global simple index has to scan all the data files. This contributes to a 2x improvement on the overall write latency, as the savings from the index lookup offsets the small additional overhead on updating the record level index. Next, we measure how record level index improves SQL latency with the point lookups. We use the store stales table and the TPC-DS 10 terabyte dataset, and we ran two types of queries, a select star for a particular record key value and a delete operation for a particular record key value. By using the record level index for filtering, we see about a 2 to 3x improvement with record level index compared to something without the record level index, so no RLI. This shows how record level index can give a great performance benefit. The record level index is available on Hudi 0.14.0 release, and we would love to hear your feedback. Actually, in the Hudi community, we've gotten some feedback on the 0.14.0 release, and also specific feedback on the record level index as well. So if you are using it and you want to tell us about your experience or maybe how your workloads have improved, please share that feedback on the Hudi community Slack. Next, we'll talk about, and so this kind of wraps up the kind of like the quick overview of the record level index and a little bit deep dive into the mechanism. If you love and use Hudi, again, please give us a star on GitHub. We're also growing really fast. We'd love for you to give us a follow on LinkedIn and Twitter, and that will also be linked down below. And again, if you are curious or want to ask more questions about the community sync or anything else about Hudi, you can join the Hudi community Slack. And there are a few of us in the Slack community that are very active, and we ensure that all questions get answered and have responses. So thank you again for being a Hudi community member, and we'll see you on November's community sync.